This lecture is being brought to you in part by the generous gifts of these sponsors.
Thank you, Lori, so much, and thank you all for the opportunity to be here. I've had an incredible day. As Lori mentioned, I got to meet some excellent students, at least one of whom is in the audience somewhere here. There she is. Hey, how's it going? Who have built experiments that are being tested or will be tested on the International Space Station, which is a pretty incredible thing. So as a scientist, as a chemist that now studies astrobiology out in the solar system, I kind of think of myself as a space detective. You know, I don't necessarily have the spacesuit and the magnifying glass, but I basically use tools to answer the same questions that a detective might. What, where, why, and how, right? So let's start with the what. What are we looking for? Well, it would be amazing if, an alien came and landed and said, hello. We haven't found that yet. And instead, we tend to use Earth examples to give us an idea of what kind of life we might find in other places in our cosmic backyard. This guy is a good example. This is a tardigrade, also known as a water bear. They're microscopic organisms that can survive in space. And they look pretty gnarly, but that's just the beginning. There are all sorts of different things, examples that we have here on Earth of weird life. And when we try to take those lessons and apply them other places, I think it's important for us to keep in mind that if we do find life for the first time in human history somewhere else, it might look very different from what we expect. And so we try to be as unbiased as possible. We call it agnostic when we search for evidence of life. Now, what are we looking for? We use the term biosignature to define the kinds of things that we look for to tell us that life is either there now or it was there in the past. And this can take many forms. It could be a molecule or set of molecules. Bonus points, anyone who knows what molecule this is? Anyone? This is ATP. It is the energy-carrying molecule, adenosine triphosphate, that all known life uses. We could also see cells, bits of cells. Who knows? Maybe there's a whale on Enceladus, and we'll get to see it, breach and be able to say, hey, definitely there's life there. But we also might see evidence of past life. This is something that the Mars Perseverance rover and many of the other missions on Mars are working to help characterize and understand if indeed some of these environments like Jezero Crater, which is where the Perseverance rover is right now, was once a habitable or inhabited environment. So we're looking for biosignatures. That's great. Well, where are we looking? Let's start with the one example, the one place where we are sure life exists, Earth. Now, we're going to try to not be biased, but perhaps we can take some lessons from our understanding of what kind of life exists here, and then we can use that to inform our searches for life elsewhere. Well, it turns out that life appears to need 3 ingredients, at least life as we know it. Now, we can talk about life as we don't know it too, but right now we're going to limit our discussion to water-based kinds of life. And if we do that, we find here on Earth that any place you have these 3 ingredients, water, chemical building blocks, the stuff that sort of makes up the molecular machinery of our cells, and energy, anytime you have those 3 ingredients, you find life here on Earth, every single time. So it would make sense then to try to search for other places in our cosmic backyard that also have those 3 key ingredients. Well, are there other places? It turns out there are, and we have a name for them. We call them ocean worlds. Now, Earth, of course, yes, we have oceans. We are an ocean world, but it turns out that we may be more the exception than the rule. Most of the other places with liquid water that we're finding in our solar system don't have that water on the surface. Instead, they have it underneath a shell of ice. These oceans tend to be global, so they cover the entire subsurface area of the moon. Typically, these are moons where this happens. Sometimes that liquid water can be in contact with the rocky interior of a moon. That can be important. We'll get into that later. Sometimes there will be a layer of what we call high pressure ice in between, and that can make it more or less likely that life could exist there. But these ocean worlds, it turns out there are a lot of them, and these aren't even all of the ones that we have discovered or we have evidence for so far. I'm going to talk about just 3 of them today, but if you have questions, I'm happy to go into some of the current understandings of a few of the others. So first, let's skip out to Jupiter. So we've gone, from the Earth, which is 1 astronomical unit away from the sun. We've done that 4 more times to get out to Jupiter. Space is big. And Jupiter is incredible. It's gorgeous. It's amazing. I'm not super interested in Jupiter itself. I'm interested in its moons. One of them in particular, this is Europa. It's smaller than Earth's moon, and it has a fascinating surface. I mean, look at this. It's got these cracks. It has ridges. It also doesn't have a lot of craters. That'll be important in a little bit. This surface is not rock. This surface is made out of water ice, similar to the ice that we have here. And if you slice it open, you can see that it has a liquid water ocean, as well as some rocky bits and some metal on the inside. And it turns out that the liquid in that ocean, if you count it all up, is about twice as much as all of the liquid oceans on our Earth combined. So that's a lot of water. Europa's not that big in comparison, and yet it seems to have this wonderfully habitable subsurface ocean. Now, why is it liquid? Jupiter is much further away from the sun, right? Everything out there should be frozen solid, but it's not. We think that there are 2 things going on that keep heats in that environment that keep that ocean liquid. One of them, we think, is what we're showing here due to the fact that Europa's orbit around Jupiter is not a perfect circle. Instead, it's slightly elliptical, which means sometimes Europa is closer to Jupiter, and sometimes it's further away. So sometimes it experiences more gravity, because Jupiter's big, right? It's the bouncer of our solar system. It's the largest planet. So sometimes when it's closer, it's feeling more gravity, and sometimes when it's further away, it feels less. And this leads to tidal flexing. So the moon basically does this on the order of several tens of meters, we think, each time it passes around Jupiter, which happens about every 3.5 days. And so that friction leads to heat, and we think that heat is part of what is keeping that ocean liquid. That heat may also drive very interesting things happening at the sea floor of Europa. Now, I wish this was a video of Europa. It's not. This is of Earth. But what you're looking at here is something called a hydrothermal vent. There are certain places at the sea floor where we have ocean water that is sucked a little bit underneath into the interior of the Earth. It gets heated up, it picks up minerals, and then when it is squirted back out into that cold ocean water, it precipitates these minerals out into these gorgeous chimneys. And so you end up having a great habitat, as you can see here, for life. Not just microbes, but shrimp, octopods. There are these tube worms that can live to be like 200 or 300 years old. It's wild. But they're living as far removed from sunlight as you can be. They're existing instead off of geothermal energy. And these are the kind of model environments we think could be present in a place like Europa, which has all of this internal heating. So Europa has water, check, box done. It has energy, and we think it also has a lot of the chemical building blocks. We know this because of some measurements that previous spacecraft have made, like Galileo. This was a mission that was launched in the 90s and did some exploration and some observations of Europa. So we think that we have all 3 of these ingredients. So now we can test a hypothesis. If you have all of the ingredients for life as you know it, and you mix them together and you wait, does life form like it has here on Earth? We can start to explore that here at Europa, but only if that evidence is getting from the ocean to the surface. So now let's go back and let's look at Europa's surface again. Remember I said that there aren't a lot of craters? Actually, this is one of the few craters. You can actually see it. Wait, I have a laser pointer right here. Now, Europa doesn't have a lot of craters. This is different from our moon, right? Our moon has a ton. It turns out that's actually really important. We use crater counts to date how old things are, with the basic idea that if something's been around longer, it's gotten whacked more times by meteorites, and so it's going to have more craters. The fact that Europa doesn't have many tells us something important. It tells us that the surface is young. And we know Jupiter's been around a long time, the moons have been around a long time, but somehow its surface is getting regenerated. It's getting refreshed over time. And it turns, if you look at the amount of craters, the number of craters that are on Europa's surface, it looks to be somewhere between 50 to 90 million years old. I know that sounds old, but in terms of the age of the solar system, it's not that long. So if T-Rex had his tiny arms, he had a telescope, and he was looking up at Europa, he or she, could be a female T-Rex, would have seen a very different surface. Now this tells us something must be happening to make those craters go away. And we see other evidence on Europa's surface of this too. We see these beautiful cracks, these large bands where it looks like things are spreading open. We see this stuff, this is what we call chaos terrain, because it's chaotic, right? It looks like someone had, some kind of floating sheet of ice and smashed it with a hammer, and the pieces broke open and shifted around and refroze. And we think, in principle, something similar, that kind of process may have happened in these areas. We also see these little bumps called lenticulae. These are not craters. Lenticulae, I think, is Latin for freckles. You should Google that, look that up, let me know if I'm right. But we think that these happen because you have a localized heating source underneath. And so it does this thing where it heats up just a little bit of the ice and kind of causes it to have this little movement that leads to these nodules on the surface. So we see a lot of examples that tell us that there could be some things that are bubbling up, bringing some of that ocean material from the subsurface and depositing it on the surface. And some very smart geochemical and geothermal modelers have done a science and shown that this can happen. Okay, great, so we can bring these things to the surface. So there are ways that if there were life in that ocean, we may be able to see some evidence of that by looking at things on the surface. We also may have evidence for a plume of material at Europa. That's something that we've seen with the Hubble telescope, but we're not going to know for sure until we go back. So let's go back to we're going to get to the why later, so let's skip over that for now and get to the how. How are we going to study this world and see if it has evidence of life or habitability? Well, that's where we at NASA dare mighty things and where we come in. We are currently building a mission right now called the Europa Clipper. Because picture a clipper ship. It's got all sorts of instruments. We're going on an adventure. We're going to sail through space, which is big, and we are going to explore Europa. This is what the spacecraft looks like. Each of those sets of panels is pretty big. They're about, well, I'm a scientist, so I work in metric, so they're like 4 meters per panel. If you count it all up, it's pretty big. For tip to tip of the deployed wings, is about the size of a basketball court. So this is a pretty big spacecraft. And it has to be, right? We're 5 times further away from the sun at Jupiter than we are at Earth, so we get a lot less sunlight. That's why the solar panels are so big. But it means that we can operate all sorts of fascinating instruments. I'm not going to go through all these. You don't have to worry about memorizing acronyms. There will not be a test later. But what I hope that you get from this is that we are using lots of different tools in our science and engineering toolbox to study different parts of Europa. Some of these instruments are basically fancy cameras that by taking a picture of the surface can tell you what kind of things are there. Some of them are the equivalent of, you sticking your head out of a car window on a rainy day, because we're in Florida, I can't use the snowy day analogy, and catching a raindrop on your tongue and finding out what that's made of. Some other instruments have more like X-ray vision or heat cameras to identify hot spots and other things on the surface. And some of them can penetrate much more deep down to help us understand how thick that ice layer is, how deep that ocean is. And all of these pieces together give us a comprehensive idea of what Europa is really like. And so I know this is a little dark, but bear with me here. This is an example of what a flyby that Europa Clipper is planning to do, what it will look like. So I mentioned the term flyby. This is important. Sometimes when we send spacecraft to places like this, we'll go into orbit around the thing we want to study, whether it's a planet or a moon. In this case, we've decided not to do that. And part of that is Jupiter's fault. Jupiter is so big and it has such a strong magnetosphere that it sucks in the solar wind, these charged particles that are coming off of the sun and they're going everywhere in the solar system. It sucks them and it slings them around and slams them into Europa's surface. Because of that, there's a lot of radiation right in the area where Europa is. Radiation is not so good for people. If you were standing on the surface of Europa, you get a lethal dose of radiation in a few hours. It's also not great for spacecraft electronics. And so our solution to that was twofold. One, we have a vault. It's actually like a big metal, looks like a bank vault, and we're putting all of our sensitive electronics in there. And the other thing we're doing is exactly what you're seeing right here. We get in, we get our data, we get out. And we're going to do that about 50 times. And so instead of orbiting around Europa, we're orbiting Jupiter itself, and we're doing these close flybys of this moon. That way we can be able to use all of our instruments, and what you can see here is we're coordinating different measurements at different times, so we're turning instruments on and off to make sure that we get as much information as we can at different points during that flyby. A lot of scientists work very hard to plan these out in advance. And we are building this, like I said, right now. In fact, you can go to europa.nasa.gov and you can see a live video feed of these amazing engineers in their bunny suits putting this thing together. It's going to be launched in October of next year, 2024, and it's going to come right out of the Cape, right here. So if you'd like to learn more, like I said, go to europa.nasa.gov and check it out, because it's a really incredible mission. There's so many cool things we're going to learn about this ocean world with this mission that's launching next year. It should arrive at Europa in like the 2030s. Space is big. But we're also daring mighty things and thinking about what might come next. Now, I did mention that there's a radiation environment at Europa, but we can handle that. If we over-engineer our spacecraft and our landers like we do with the Mars rovers, we can have them handle something like that. This is a Europa lander concept that we have been working on at JPL, the Jet Propulsion Lab, that would be able to land, could handle that radiation environment, could cut into the surface. You'll see a little arm come out in a bit with these two gnarly-looking saw blades to collect more of that surface sample and bring it in and look at it with special instruments. Now, this ice is not like the ice in your freezer. It is much, much colder, and it tends to have similar properties to certain rocks like granite at these very cold temperatures. On top of that, metal is much more brittle at low temperatures. And so the engineers who were working on this had to devise very special alloys and special cutting tools. They did a lot of testing to be sure that it wouldn't break or get stuck or anything like that. As well, we wanted to make sure that we could handle, or we would not chemically or physically alter that sample too much. We didn't want to heat it up. We didn't want to give it an opportunity to change between when we collected it and when we brought it into the spacecraft. And so this mission concept, as well as many others, are being prepared for the future for what comes after Clipper. Okay, so that's one ocean world. I told you I was going to talk about 3. 1 is down. Now let's go to Saturn, which, if you ever have that poster, does anyone of like all the planets that are evenly spaced out in the solar system, they're not actually like that, right? Like the distance that you have to go from the sun to Jupiter, you have to do that again to get to Saturn. Space is big. So we've done that in the blink of an eye. Now we're out here hanging out with Saturn, which is just gorgeous. My first mission I ever got to work on at JPL was the Cassini mission, which was in the Saturn system for 13 years, exploring this planet, its rings, and its moons. And I'm going to talk about 2 of them. The first one, you can actually see in this image, this is real to scale. Okay, Saturn may not be quite as big as Jupiter, it's pretty big. And this moon is, it's not a speck. It's a decent size compared to the size of the planet Saturn, which is pretty amazing. Titan, it's actually the biggest moon in the solar system if you count its atmosphere. If you strip its atmosphere away, then Ganymede gets a win, and that's fine. We'll let Ganymede have that. Ganymede's a moon around Jupiter. Because Titan is just so fascinating. You heard me, it has an atmosphere. It's a moon with an atmosphere, and it's actually an atmosphere that's thicker than Earth's. Because its gravity is less, it's about the same gravity as Earth's moon, and because its atmosphere is denser, if you were standing on the surface of Titan and you had wings and you flapped them, you could fly. That'll be important later. This is one of my most favorite images of Titan. This was taken by the Cassini spacecraft, and it was taken in the infrared, which are wavelengths that could go through that thick atmosphere. I live in Los Angeles now. We're used to smog and haze. Titan has a lot of that for not automobiles, but basically the same reasons. It's because of UV that happens. But in the infrared, you can peer through that haze, and what you're looking at there is a glint of sunlight off of something. The only time sunlight glints like that is if it's hitting something very smooth, smoother than any solid surface. It's hitting liquid. But at these temperatures, we're much further out than Jupiter now. That liquid could not be water. So what is it? Well, whatever it is, it makes clouds. Just like Earth, Titan has clouds. They're made out of different stuff. Titan has rivers. That liquid is carving, it's etching channels into Titan's surface. And that liquid actually pools into lakes at the poles that are pretty big. But these are not liquid water. These are, in fact, liquid methane and ethane, hydrocarbons. So if you go back to high school chemistry, you remember learning about like dissolves like, and water. Water is a polar liquid. Right? So polar things dissolve in water. This is a non-polar liquid. So oil in water doesn't work so much. Oil in here, great, golden. This dissolves things that are very different from what liquid water does. And so we were talking before about life as we know it that requires liquid water. Boy, is it fun as an astrobiologist to explore what kind of life could exist in a liquid methane lake, because it's wild and very different, and we're still just scratching the surface. So Titan has lakes. It has dunes. These dunes are also made out of different stuff than our dunes here on Earth. We think are made of organic molecules, lots of different combinations of carbon, hydrogen, and nitrogen. And so we have a picture of a world that is similar to Earth in many ways, and yet it's made of different stuff. Oh, and I also forgot to mention, this one also has a liquid water ocean underneath all that cool stuff that's happening on the surface. This is a fascinating place to study. Cassini was able to do it from orbit, but peering through that haze layer was pretty challenging. Boy, wouldn't it be nice if we were designing something that could go and explore this incredible environment and give us, this is an artist concept, but give us images like this. Turns out we are. Picture one of those large rovers, the big ones, the ones that are size of a car, like Perseverance that I work on. Take its wheels off, give it skis, and then give it 4 sets of 2 counter-rotating helicopter blades. This is Dragonfly. Who had the Dragonfly necklace? Where'd she go? She's here. Yes. I told you that would be important later. We are building this now. It's going to launch in 2027. It'll arrive to Titan around 2034. Again, space is big. With the goal of landing and then being able to relocate through this ability to fly. And so we call this a relocatable lander. It is a rotorcraft, but it's going to spend most of its time on the surface of Titan. Dragonfly has many goals for its science mission. Most of them are to characterize this environment, to understand what kind of organic molecules are there. Could prebiotic chemistry be possible? Or even further, is biotic chemistry happening there? We'll be able to make science measurements mostly when landed, but also in flight. We'll be able to give you a weather report for the surface of Titan, including relative humidity. of methane. Yeah. And this is where we're going to land. We decided that it would be smart to land in a place that is near a crater. Now, Titan, similar to Europa, doesn't have very many craters. Here, though, we think a lot of that is because of its very thick atmosphere. So just like on Earth, a lot of times you'll see a beautiful, meteor kind of go through and you see it burn up. The same thing happens on Titan. So not many, only really big meteoritic, things moving through the atmosphere will lead to impacts on the surface. And one of them is this crater called Selk crater. And so we decided it would be smart to land near this because we can, let me back up for a second, because that crater has done some work for us. We think that there are a bunch of organic molecules in these dunes and things on the surface, but we also want to study what the bedrock is made out of. And this impact has excavated that for us. So it's a great place where we can look at some of these dunes and interdune materials, but also some of the stuff that is in and around that crater. So we kind of get our cake and eat it too. Now, we came up with a strategy for how we would be able to assess future landing sites because the communication between Earth and Saturn, light takes between 68 to 86 minutes to go that far. So about an hour, one way, right? And then you got to wait. So you're like, are you okay? Wait an hour. Wait an hour again. Yes, I'm okay. We can't joystick. No one's going to be here on Earth flying Dragonfly. It's going to fly itself. And it also has to make decisions on its own. And so what we decided the best way to do this was to always have our future plans for where we want to land, being able to scope out candidate landing sites as we are in flight before we go and land in something we've already characterized. And so the idea here is that we will have time to have scientists and engineers in the loop on Earth evaluating some of these images for science potential, right? Is this a scientifically interesting site? As well as the engineers going, is it safe to land? Because this is the most fun part of working for NASA. The scientists want to go to the interesting places, the engineers want to go to the safe places, and you need to find where that Venn diagram actually overlaps. And so that's what we'll be doing as we're assessing candidate landing sites. And then we'll go back to one that we've already surveyed before. So what are we going to do? Well, in addition to the weather report and a seismometer, a few other things that you like to have when you've landed on a surface, we also have a sampling system that will be able to collect material from the surface. And since this place has an atmosphere, we can use what is essentially a fancy vacuum cleaner to suck up some of those grains and materials and deposit them in these sample cups. From there, we have special instruments like mass spectrometers that are able to characterize what kind of molecules are there. Not only that, but we also have a special instrument that will be able to do a very critical life test. This is something that we call chirality. Certain molecules that are present in our bodies and all known life tend to only, there are two different kinds, and all known life tends to use only one of them. So this is a great test against an abiotic case where no life is. Anytime you have that kind of chemistry, you make both types. And so this is one of those life tests that we'll be bringing with us. But it's going to require all of the payload, a whole lot of different instruments working in synergy together for us to form a complete picture of what is going on this fascinating moon, Titan. So if you'd like to learn more, go to dragonfly.Johns Hopkins University Applied Physics Lab.edu and you can learn more. Okay, how are we doing on time? Good, we have time. All right, so we are 2 down. Last fascinating moon to go, and I love them all. I can't really pick a favorite, but this one's pretty amazing. This is also in orbit around Saturn. This is Enceladus, and this is a real image that Cassini took that's backlit by the sun. And you see that stuff coming out of the South Pole? What is that? What is that? That is a plume. It's a plume of material coming out of these 4 giant cracks in the South Pole. We call them the tiger stripes because it looks like a giant tiger went like that. And they're large rifts, and out of that is streaming material from its subsurface ocean. So it's kind of the universe's way of saying, hey, NASA, got a liquid water ocean here. You want to see if there's any life? Come on by. Just fly through. Grab some free sample right here at Enceladus. And so Cassini discovered this and was also able to make some more measurements to help us characterize the thickness of that ice shell, the depth of the ocean, and a few other things. Now, I had mentioned before that Europa around Jupiter may have hydrothermal vents. Well, here we have 3 separate lines of evidence of characteristic molecules, things that are coming out in that plume that tell us that we really do think that's what's going on here. And we get free sample from that ocean coming out into space. Cassini flew through this plume of material multiple times, but it was not designed to look for life. It did give us some tantalizing evidence, though, that make us want to go back. Cassini had 2 instruments on board, one that looked at the gas, so the small molecules in the plume, and one that looked at the ice grains. So as soon as that water, hits the cold vacuum of space, it freezes and makes these little ice grains. Let's look at the gas first. Now in the gas, we found water, duh, okay, that's great. But we also found things like methane, hydrogen gas. These are things that either microbes eat or they poop out. That's pretty exciting. We also found simple and what I'm calling complex organic molecules, but keep in mind that Cassini was not meant to look for large, proteins or DNA or things that are really characteristic of life. In fact, the smallest amino acid that makes up our proteins has a mass of 75, so it might be buried in here somewhere, but anything bigger than that, we wouldn't be able to see with this instrument. It wasn't designed to look for this. When we built Cassini, we thought that everything out in the Saturn system was cold and dead and kind of boring. And so we built instruments that could understand the very simple molecules that we expected to be there. We had no idea this exciting and dynamic kind of world existed. Now we do, and we definitely want to go back. So that was the gas. Well, what about those ice grains? Again, we found lots of water ice, duh, but we also found salt. In fact, we think that this liquid water ocean is almost as salty as Earth's ocean. We found about 0.5 to 2% by weight salt. Earth's ocean is about 3, so in the same ballpark. We also found organic molecules. But again, this instrument was not meant to look for biosignatures. It gave us a taste, a hint of what's there, but it really is going to take another mission to go back and characterize that some more. Now, I'd mentioned that we saw some molecules that indicated hydrothermal activity. One of them, the most important in my opinion, is something called SiO2. This is silica. Now, you may see this, we have this a lot on Earth as well. But because this is silica, not silicate, which is SiO4, and because the size of the particles that are ejected out of Enceladus's plume are a very particular size, the only way that you can make those is if you have liquid water in contact with a rocky interior at temperatures of 90 degrees C or above. That's almost the boiling point of water. So that's pretty warm. And we have examples of this here on Earth. The video of hydrothermal vents I showed you earlier, that was something we call a black smoker. Those tend to be really hot, like 350 C. This image you can see here, this is a different hydrothermal vent that's a little bit cooler. It's around those same temperatures, like 90 to 100-ish Celsius. So these are the kinds of environments that we think are good analogs for what may be happening on Enceladus. And we find tons of life there too. Okay, so Cassini was our first step. What do we do next? Well, there are a lot of different options. Some of them involve accessing the ocean itself. Those are the blue arrows. But you can do a lot just by collecting some of that free plume sample and analyzing that. And there are a few mission concepts that are being worked on right now to do just that. But we at JPL, we dare mighty things. And so we were thinking, boy, flying through the plume is great, but wouldn't it be nice to get down into one of those cracks and stick our face like right in the ocean and really just look and see what's there? And so that's what we're working on. We love our acronyms. This one's called EELS. You'll see why in just a second. This is a robot that's different from any of the others I've shown you before. Instead of a traditional rover or a helicopter, we wanted something that could get down into that crevasse. Remember, gas and grains are shooting up at pretty high speeds, about 200 meters a second. You've got to be able to counteract, push against those forces to go down. And we expect that some parts of this conduit may be really constrained. So we can't have a very large, wide kind of robotic explorer. We need something small, something thin, something like an eel to be able to get down into that ocean. Now, when we had originally done this video a couple of years ago, we were planning our field tests, which we did this last fall. And so this is what the rover or the robot looks like now, today. We still have a lot of those same snake-like segments you could see before. The head looks a little different. Part of that is because of the way that it sees. It uses things like LiDAR, so essentially lasers bouncing off things, kind of like echolocation like a bat does, to be able to make a map. It includes some cameras as well. Science payload, hooray, that's me, I'm excited about that. And then it has all of these other ways to be able to move. Now, remember I said that we can't fly Dragonfly by itself. It has to, or we can't fly it here from Earth. It has to be able to fly itself. It has to be autonomous. The same thing is true of eels. It also has to be able to move, to make decisions, move around obstacles, all on its own. And so we've been working very hard on something we call proprioception, which is basically its way of perceiving its environment, reacting to it, and achieving a goal, which could be to, slither from here to there. It could be go down into the vents and collect ocean samples and discover if we are truly alone in the universe for the first time in human history. That would be great. So we're working on that. Let's see, a few other things that are important. Yeah, depending on how, so the way that this snake moves is it has these screw blades on the outside of each segment, and by rotating those in different ways, you can actually get different gaits. And so you'll see in the next video I'm about to show you that was just cleared. You're the first ones who get to see this, so this is kind of exciting, that it can move around in different ways, kind of like how snakes have, they can slither, they can do sidewinding and other things. We're starting to adapt some of those examples from nature into this concept. And so each of these modules is important as we learn how to drive or how to move like a snake does. Okay, and so these are a few examples of some of the tests that we've done, and you'll see it'll look different in some of these depending on what parts of the rover or the robot we're testing. First, we started off at the Pasadena ice rink. They were kind enough to let us go there at like 5 in the morning so that we could do some tests on real ice. We've also been doing lots of tests in a lab. Now here, it may not look like ice, but a lot of these materials we're using have very similar properties. There's this surface material you can buy that ice skaters will train on in the summertime because it has a lot of the same properties, so we've used that. We also went up to Canada. There's a lovely glacier there where we could do some tests. And this is our Mars yard at JPL, where oftentimes you'll have a Mars rover driving in the background. So, ignore that, focus on the snake. But this is where we can test a lot of these different gaits and see how this kind of robotic architecture will behave in a real environment. So this is part of that proprioception where we programmed it to go from point A to point B, and it was using that LiDAR, that echolocation, but with lasers, to be able to navigate around obstacles. So this has been a very fun project to work on. It's a little bit terrifying to see this thing move by itself. You're about to see, yes, Cobra mode, look at that. And when it turns and it looks at you and you're like, hello, it's a very large metal snake that's hopefully going to find life somewhere else one day. So we're daring mighty things. We're testing out all of these because this is the goal, right? To be able to see a new robot that has different ways to access environments that we didn't dream possible even a few years ago. So I want to close with something that Carl Sagan said. So Carl Sagan, of course, famous scientist, incredible human, and was pivotal in the first 2 landers on Mars, the Viking landers. And in his book Cosmos, he talked about how frustrating it was to finally get to this alien world, this new environment, and not be able to move, right? Because who knows, that key biosignature that we are searching for could be just behind that rock right over there. And so that's why it's so important to develop these mobility systems, these different ways to be able to extend our senses through these robotic explorers to other places in the solar system. So we went through the what, the where, and the how, but now I'll just leave you with one picture for the why. This is kind of hard to see, but really the piece that you can see is the most important. This is the famous pale blue dot image. This is a photo that Voyager took as it was leaving our solar system, and that is Earth, that tiny little bitty, everyone you have ever known or has ever lived in history is all right there. And from an astrobiology perspective, this excites me and also terrifies me, because that is all, or one example of life. That's it. And that one tiny place. And we are finally now at the point where we have technology. We can really test this hypothesis. If you have water, chemistry, and energy, and you mix them all together and you wait, does life form? I really hope the answer is yes. Otherwise, we're really horribly, terribly alone. I hope that's not the answer. But we can finally start to test that for real in our own cosmic backyard. And as a scientist at NASA, it's such a tremendous privilege to be able to work with teams that are doing this. So with that, thank you so much for your attention. Again, I am talking about work that a lot of people have done, but I would be very happy to take your questions. So thank you. I'm going to leave that up because I think it's just so inspiring.
So y'all make sure I'm going to toss this to you, and then y'all toss it back. Okay.
Thank you. That was great, Dr. Cable. It's great seeing such enthusiastic and smart people working on these problems for us.
Thank you.
You know, here on Earth in the deep sea hydrothermal vents, obviously the base of the food chain there is chemosynthetic bacteria.
Yes.
And they're taking these reduced compounds and using that energy to get their metabolism going. When you go to a water-based system like you would find on Europa, I'm sure you're expecting to find these chemosynthetic bacteria. Can you speculate on whether there might be multicellular organisms that can feed on these bacteria?
That is a great question. Yes. So what was your name?
Jerry Cheney.
Thank you, Jerry. So as Jerry mentioned, these ecosystems, they tend to start at the microbial level, right? That there are organisms that will utilize these redox, so reduced oxidized chemistry gradients, to be able to, essentially what they do is they just shuttle electrons from a place that's electron rich to a place that's electron poor, and they just put a little tax on that, and that's the energy they use to be alive. And this can come in many different forms. You can, oxidize or reduce things like methane, molecular hydrogen, other chemicals that are present. And then once those microorganisms fill up that niche, now what they're eating, what they're leaving behind, can start to build a more complex ecosystem where you could envision having those tube worms and the shrimp and the crabs and the other things that you saw in these hydrothermal systems. And we do think that in some of these environments there may be enough energy to do that. But again, we only have Earth as an example. And so what some scientists will do is they will take what they call the energy budget of a world like Europa. So they do some math to figure out, okay, that tidal heating is leading to a certain amount of energy. Okay, we can check that off. There may be other energy from something called radiogenic heating. It's the same thing that keeps our core hot. Radioactive elements decay over time and they generate heat. And so you add up all those things and then you figure out how much of that energy would be available to fuel a community of organisms in the ocean. The problem is we make so many assumptions along the way that our error bars are really big. Our current guesses for the amount of cells that could exist in here ranges from 1 cell per mil to millions. And to give you an example, Earth's seawater has about 1 million cells per mil. And so it varies a lot. Our solution then is, okay, well, let's design instruments that can handle as much of that as possible. And so we tend to test a lot of our instruments in some of the most energy-limited environments here on Earth. There are a few subglacial lakes, like Lake Vostok, very famously, is down in the Antarctic. It's underneath a glacier, so it's isolated as pretty well as you can be from sunlight. And there we find pretty dilute cells, about 1,000 cells per mil. So 3 orders of magnitude less than Earth's oceans. And so we get water from those environments and we test our instruments and see how they do. Or we can generate, artificially diluted environments or samples in the lab and test how they do, with the goal of trying to be able to get down to, even if they're maybe not one cell in the whole ocean, but if there was a really dilute population of life, we would still be able to find evidence of it. And it's a challenge. It's something that we're working on, and we're getting better and better with our techniques and our instruments that we're building. It was a great question.
Next. Oh, here we go. Can I toss you?
Since it's taking years to get to these places, and technology is getting so AI, things like that, how frustrating is it that that when these things get there, there's going to be so much more things that you could have done to test some of this stuff?
That is a really great point, especially when you think about most of these missions, like Cassini, for example, when you really count from the beginning, the first time that a proposal was put together to say, hey, let's send a mission to go to Saturn, and this is what it should do. That, from there to when Cassini was actually built and launched, was probably about 20, 25 years. So a lot of these, they take a while because it takes the community to build up support. And by community, I mean mostly planetary scientists, astrobiologists saying, hey, this is a priority, we should go here. And then, we need to get the funding to be able to build it. In some cases, we need to be able to develop the technology. And so by the time it gets to the launch pad, you're exactly right. A lot of these instruments are obsolete's too strong of a term, but they're outdated by then because it takes some time to be able to get them to handle the radiation environment, to handle the extremes we expect in these places. But I look at my contribution as a scientist to this field, and I think about it as, not okay, we're building up, we've done this thing, and now we've achieved our goal. It's taking steps. Right? Viking was a step. Voyager was a step. Galileo, which took this image of Europa, was a step. And Europa Clipper will be the next step. Dragonfly will be the next step. This robotic snake EELS, hopefully I will get to see that in my lifetime. But even if I don't, even if all we're doing is proving the technology works here on Earth, and that may come, a few decades after I'm no longer here, I still helped make it, and it's still going on. And so a piece of me is going to live on in these missions and in the answers to these critical questions. And so to me, that's part of what's so amazing about the process, is contributing to something larger than yourself.
Awesome. Next? Yep. Oh, I see you. Okay.
One of the surface features on Europa that you showed looked indicative, at least to a couple of metallurgists, of shock-induced deformation twinning or perhaps solidification twinning.
Okay, stop me when... That one?
Yeah, that one, previous, yeah. Nope.
That
There you
one,
go.
okay.
Yeah, I don't know what the scale is.
Kilometers, multiples of, or tens of kilometers or bigger. Yeah, the
Okay.
chaos terrain, you can look up a lot of different papers about it. We think that most of them are associated with, now I know I can get a little bit technical with some of you, diapurism, potentially something like this, but maybe much more localized, where you have heating source underneath, and maybe it's a hydrothermal event or something similar, but you end up with heating at the base of the ice shell, so the top of the ocean, bottom of the ice shell, and then that makes some of the ice a little bit more ductile. It can flow more easily, and so that we think can reach all the way up to the surface potentially. But there are still a lot of things we don't understand about this environment. And boy, some of our sort of terrestrial geologists have shifted over and are starting to work purely in ice now. And rheology has become more of a popular term. That's another one cool thing I forgot to mention, because now we're talking about ocean worlds, right? Liquid water, a lot of our teams are bleeding in and pulling in people from fields like marine biology and oceanography and things like that. So it's been really lovely to start to form bridges and pull in members of the community who before would never have thought that them studying, a hydrothermal system or reefs or a certain species of fish that lives in an energy-limited environment, that their insights would be helpful designing a mission to go to a moon of Jupiter. So it's been a lot of fun to see the community of scientists that we involve in these expand and grow over time. These are great questions.
You mentioned methane so many times. I have no idea of how that would affect a human organism, where it comes from, what it does, and so forth.
Methane?
Yes.
Yeah, well, you would freeze to death first. That would be bad. The surface of Titan is minus 183 degrees Celsius. So what is that in Fahrenheit? Someone do that really quick. I don't work in Fahrenheit. It's very, very cold. So liquid nitrogen is minus, it's 79 Kelvin. So what is that, minus 196? Minus 196 Celsius. Titan is just a little bit warmer than that. So if you've ever seen any of those demos where someone will take liquid nitrogen and freeze a rose and smash it, we're talking like 5 degrees warmer than that is Titan's surface. That being said, because you have a thick atmosphere, you wouldn't need a spacesuit on Titan. You would need a heck of a parka, like no exposed skin, and you'd have to bring your own oxygen, but you could happily, walk around on the surface without a giant spacesuit. But these solvents would probably not be healthy for you to have on your skin. The closest example is, so methane is a single carbon molecule with some hydrogens around, or a single carbon atom with hydrogens around. You can start to make it bigger by attaching more carbon. So ethane comes next, that's 2, then propane. The closest thing you can get to that's liquid here on Earth at our temperatures is hexanes. So that's 6 carbons. And that's a solvent that you can, use to dissolve paint, and it's just not good for your skin. It's really bad. So as a chemist, there's a saying, there are old chemists, there are bold chemists, there are no old, bold chemists. I plan to live a long time, so I'm very careful in the laboratory. So we will actually take, because this is just a little bit warmer than liquid nitrogen temperatures, it's actually ideal for us to work in the lab. And I don't know if I brought any, I don't think I have any slides on that specifically, but what we'll do is essentially recreate this in the laboratory. You take a liquid nitrogen bath, and you do a little bit of a thermal buffer so you can heat it up a bit more than that. And then you can condense methane, ethane, and make a mini Titan lake right in your own laboratory. And then we dissolve different things in there to try to understand what kind of chemistry can happen. This is cold. Typically, in cold environments, a lot of chemical reactions will slow down or stop completely. But what we're finding is that some spontaneous chemistry still happens, even at these low temperatures. You can make and break covalent bonds, which is a surprise. And half the time when we mix together, even just 2 simple molecules that we think are present on Titan, we'll find something new. We're discovering these new minerals and new ways that they associate, that they attach together, that may be important for prebiotic chemistry. Now, we haven't made a cell yet that would happily exist in a liquid methane lake, but we're starting to understand the steps that would be required from a chemistry perspective to get there. And if you want to hang around after, maybe I can dig up a couple of images of the work that we've been doing in the lab.
Very informative talk. This may be a bit unfair because we're kind of locked in our solar system.
True.
But many of us are, or at least some of us, are very interested in the search for life on TRAPPIST-1, which has 3 or 4 planets in the Goldilocks zone, and also mimics the plant life and life on Earth with the orbits of its planets being in Fibonacci sequence.
Ooh.
Could you comment?
I can, yes. Okay, wow, you guys are, these are great questions. Okay, so the TRAPPIST system is, I forget exactly how far away it is, but it's one of the systems that we've been characterizing with some of our telescope missions to look for and categorize exoplanets. So these are planets in orbit around other stars. The TRAPPIST system is uniquely important to us because it has, what was your name? as Scott said, thank you, Scott, for the question, multiple planets in what they call the habitable zone or the Goldilocks zone. This is the same place where Earth is in orbit around our star. It's a place where liquid can be stable on the surface. Of course, that's very exciting because essentially that means that these planets are Earth-like, at least in many respects. We've characterized their mass, we know they're rocky, and we're pretty sure that they have water, or at least a condition suitable for water. The next step is to take future missions or current missions that are up there, like James Webb Space Telescope, point that at them, and really try to understand what kind of chemical building blocks could be present there. Now, these missions are great for studying those worlds. It would be much harder to look, say, for a Titan or a Europa or Enceladus, where some of those, what we think are key ingredients for life, may be hidden under an ice shell. That's more challenging. But we can still start to characterize these other unique solar systems and what their potential could be for life as we know it or life as we don't know it. Now, the question about the Fibonacci sequence, I don't know the exact rotational periods of all those planets. So what I do know is even here in our own solar system, Europa has a unique periodicity with some of the other moons in orbit around Jupiter, and this has to do with something called resonance. So if the plant is Jupiter, right, the next moon out is Io. It's the most volcanically active body in the solar system. It's fascinating for reasons not related to astrobiology, so I didn't talk about it today. Io, then Europa, then Ganymede, biggest moon in the solar system. Yes, you get a win. And then Callisto. And Callisto isn't quite as involved in the resonance as much as the other three, but for every, okay, let me get this right. For every one orbit Europa does, Io does 2. For every one orbit Ganymede does, Europa does 2. And so it has a 1, 2, 4 resonance. And part of that we think has to do with orbital mechanics and the way these bodies kind of stabilize to get into that kind of an orbit. Now the Fibonacci sequence also has a similar kind of, 1 + 1 is 2, you add those together, you get 3, and then you get 5, and you keep going. And so it could be that a similar kind of resonance is happening. But what orbital mechanics is hard. Once you get past what they call the two-body problem, once you introduce 3 things together, we actually can't solve those equations anymore. You have to use approximations. And so when you get into really complex systems, it can get tricky. But hopefully, as computers get more and more advanced, we'll get better at being able to characterize those systems. Because it's a really fascinating time to be alive, we have, I think, now counted up to 5,000 exoplanets, and something like 27, it may be more since I last checked. So was she going to Google things? Did she leave? Someone should, are Earth-like, and that includes some in the TRAPPIST system. So that count is just going to go up and up because we've only just started to look in the last few years.
So y'all, we have time for one more question.
I'll hang around too. So
okay.
Yes.
You come up front afterwards, and I'll get with you. I know you've had your hand up for a minute.
Thank you. First, let me say thank you for your service. This is a wonderful talk.
Thank you.
In case of Europa, you mentioned tidal friction is the source of energy.
Yes.
On these other 2 moons, what do we think is the source?
Great question. We think a lot of it is the same, that same tidal flexing. For Enceladus, there's a pretty strong ellipticity. Its orbit is very elliptical, and which we also see because that the heating, the tiger stripes that are the place where the plume is coming out from, it's not symmetrical, right? We don't see something on the North Pole as well that's a hot spot too, which is kind of weird. And so we think that there could be something called North Polar Wander, that over time its shell may have shifted. There could have been an impact. There are a lot of discussions about why that particular spot is hot and things are coming out of there. But yeah, for most of these, it's 2 things actually. It's that tidal flexing I talked about, the frictional heating, and radiogenic heating. I mentioned it a little while ago. So radioactive elements decaying over time. We think those 2 things contribute together and lead to the heating that we see that keeps the oceans liquid. It's a great question.
So I would like to thank Morgan for coming across the country to be with us tonight.